Hello everyone. I wanted to do this video, like I said, in class. So on Wednesday we can just focus on reviewing for the exam. And so we did get started already in section 2.2. So let's just go right where we left off. Okay, so let me also say that for those who are watching this video, that I'm going to post 3 questions throughout this video for you to answer and bring to class on Wednesday. And if you do get them correct, they can be worth 3 extra credit points on the exam. So again, you need to make sure you watch this entire video to get the questions, but there will be 3 questions. Okay? All right, so this is where we left off in class, and this right here we talked about if A times D minus BC, and this is actually called, so there's a formal name for that. It's called the determinant, and the notation is DETA. That's notation for the determinant of matrix A, and that equals AD minus BC. And recall we talked about in class that if A is invertible, then that means it's non-singular. It's a non-singular matrix. And if A is not invertible, we call it a singular matrix. Okay, and so we found, because in this example, AD minus BC equal, what was it? So 1 times 5 is 5 minus 6, so -1, which does not equal 0. That means it's invertible or a non-singular matrix. And we actually found the inverse by using this formula over here that works for a 2 by 2 matrix, okay? And I want to check our answer by taking A times A inverse. And if that's its proper inverse, it should equal the identity matrix I2 in this case, since we have a 2 by 2 matrix, right? And so let's see, we have A, which is 1, 3, 2, 5 times A inverse -5, 3, 2, -1. So since these are both 2 by 2 matrices, we're going to end up with a 2 by 2 matrix. And so again, so if we take this first row times this first column, so that's 5, -5, plus 6, so that's 1. And then this row times this column, and so that's 1 minus 2, which is 0. And then this row times this first column here, and that's -15 plus 15, 0. And then this row times this column, which will give us 6 minus 5, which is 1. So it equals the identity matrix. So the first question that I want you to turn in is, remember I said when you're asked to show if something is an inverse matrix, then you have to not only show that A times A inverse equals the identity matrix, but that A inverse times A equals the identity matrix. So your first question is to show with the example below that A inverse times A also equals the identity matrix. Okay, so now on our next slide, we have a very, very nice matrix equations, or a very, very nice way to use, I should say, our inverse. And that is here. So if we have, well, let me see, if we have, we know this is a linear system, right? AX equals B. And now that we know about inverse, this second line tells us that if we take, I don't like that marker, if we take A inverse on both sides of that, then we can use our associative property, put those two together, and that equals the identity matrix times X. And so X, the vector X that we all try to solve for, is actually equal to A inverse times B, which is really, really nice. It's a nice fact. If we know, so that's saying if we know A, matrix A is invertible, meaning it has an inverse, it's non-singular, then to find if we're solving a system of if we're solving a linear system, I should say, if we're solving a system, then we could just take A inverse and multiply it by our vector B, and that will give us our solution. That's so cool. Okay, I enjoy that. All right, so here we have A, which, oh, it's over here, so A, and that's our vector B. Okay, and so we already solved on the last page that inverse was -5, 3, 2, -1. And so now x inverse is just, vector x is just A inverse times vector B, which equals -5, 3, 2, -1 times vector B, which is 4, 7. And this is a 2 by 2 times a 2 by 1. So we end up with a 2 by 1, which is our vector. Okay, and we do some arithmetic there. And so we end up with -6, 5. So you should stop the video to make sure that's what you get for your correct answer. But that's what we have for there. Okay. And so a nice fact to keep in mind is that this matrix inverse is unique. So if A is an n by n, so we have a square matrix, an invertible, let me rephrase, theorem. If A is an invertible, non-singular, that's another word for non-singular, n by n matrix, then for each vector B in Rn, Ax equals B has the unique solution x, vector x equals A inverse times vector B. All right, so again, if you have an invertible n by n matrix, then that's a unique solution. It has the unique solution of A inverse times B. Okay, and so we have properties. So there's more properties. So we have properties for invertible matrices. And so we have an invertible matrix n by n matrices. If A and B are invertible, then A inverse is also invertible, and A inverse is A. Okay, that sort of makes sense. And then we have A transpose is invertible. If A is invertible, then its transpose is invertible, and A transpose inverse equals A inverse transpose. Okay, and then here, you want to be careful here, so be very careful. A times B is invertible, and A times B, its inverse is equal to B inverse A inverse. And so notice the switch here. Read your book to find out more about that switch. It's an interesting switch, because you would think, well, why isn't it equal to A inverse times B inverse? There's a reason why. And so read your book for that question. Okay, so now we can look at a connection between the matrix inverse and our elementary row operations. So here, in these three examples, so what is an elementary matrix? Okay, that's a matrix that is obtained by performing one elementary row operation on the identity matrix. So here you can see that, of course, we're talking about, in all these examples, we're talking about identity matrix 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so we are in I3 is what we're talking about. And here in this first elementary row operation, and so again, it's only obtained by just one elementary row operation on your identity matrix. Okay, so it's only one. So in this first example here, E1, we see that row 2 and row 3 were switched. And I haven't used this notation, but this is another notation to switch when you're switching rows, when you're doing ERO. Okay. And then the second, all right, so you guys can see that, right? You guys see that row 2 and row 3 have been switched. Okay, so that's what's going on there. And then in the second example, what's going on with the original identity matrix? Well, here, the second example, it looks like we took 2 times row 3 and added it to row 1, and that gave us a new row 1. Okay, so 2 times row 3 plus row 1 gave us a new row 1. And so again, this is an example of an elementary row operation, because it was just one operation, one elementary row operation on this matrix on the identity matrix. And then last, what does it look like? Well, it looks like here we took 3 times R2 and produced a new R2. Okay. Okay. And again, it's just one single elementary row operation. So these 3 examples are elementary matrices. Okay, these 1, 2, and 3 are elementary matrix. Okay. Okay, so again, let's consider E1 and E3 from the last slide. And let's find, so we have this matrix here given, and let's find E1. Okay, so let's find E1 of A. Okay, well will equal again, E1 is 1, 0, 0, 0, 0, 1, 0, 1, 0. Okay, and A is 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. If we multiply, so they're both 3 by 3 matrices, so we'll end up with a 3 by 3 matrix. And if we look to see, so this first row times that, so if we do elementary row operations, we're going to get 1, 1, 1. So you can double check this. So you can stop the video and double check this. I'm just doing this to save time. And that's what our matrix is. I'm sorry, my OCD won't let me have that equal red and blue. Okay. So that's what that matrix is. And notice what's going on. Something very cool is going on here. And that is, notice that what we did was actually switch row 2 and row 3, and that's what actually happened to our elementary matrix. So multiplying an elementary matrix by another matrix performs that elementary matrix on the as your result. You see that? Because that's what happened in our final matrix. Row 2 and row 3 was switched. Isn't that cool? I just think that's really cool. So now the second question that I want you to do is to multiply E3 times E1A, which we just saw for here, and see what happens to that. And you should see something cool happening to that. So that's the second question I want you to turn in. All right, so we're actually we have a few more slides left, so a couple more slides, not too many. So elementary matrices are invertible. So elementary matrix E is invertible, and its inverse is the elementary matrix. It's the elementary matrix that transforms E back to, or E to, the identity matrix. So I'm gonna leave that first example alone, but I'm gonna look at the second example, and we see that what we did before, recall that we took 2 times row 3 and added it to row 1 to get that matrix. And so in order to take this matrix back, we need to take -2 row 3 and add it to row 1. Okay, and remember, we're doing this to the identity matrix. So if we take, so let me make sure we're clear on this. So this, I don't want to do it that way. This is being done to the identity matrix. In this case, it's I3. So that means its inverse will be 1, 0, -2, 0, 1, 0, 0, 0, 1. Okay? And let's look at E3. Okay? And that will be, well, what did we do here? So what we did was we took 3 times row 2, to create a new row 2. Okay, so what we need to do to the identity matrix is multiply row 2 by a third, right? And that'll get us back to the identity matrix. And so that means E3's inverse will equal 1 0 0 0 1/3 0 0 0 1. Okay. And you can check these to make sure by multiplying them together to make sure that they're inverses of each other. And so the third question I want you to do is to tell me, find that the inverse of that elementary matrix. Okay? And so, but we have a new method for finding a matrix. So what if you have a matrix that's, it's invertible, but it's not 2 by 2? Well, actually, how will you determine if it's invertible if it's not a 2 by 2? That's a good question. And let's talk about that. So this theorem says that we have an n by n matrix A is invertible if and only if, which means it goes both ways, A is row equivalent to the identity matrix. And so the sequence of elementary row operations that reduces A to I transforms our identity matrix into A inverse. And so another way we can look at that is we can put our matrix A together with its respective identity matrix, and through some elementary row operations, transforming it into A inverse. And if we can do that, then we have an inverse for A. Okay? And so I believe this is the last slide. And so we're going to use the theorem to find the inverse of 1 3 2 5. We already know because we found it already. And so again, we take A, we're setting up a matrix with A and the identity matrix in this case, which would be I2. And we want to, through elementary row operations, translate that. Oh, I don't want to use the word translate since we're talking about transformation, but we want to somehow create the identity matrix, and then we will have our inverse. Okay, so if you want, you can stop and write this down. I just wanted to save time. So here we have, this is where you would set it up. So you have the matrix A to the left, and then your identity matrix for a 2 by 2 matrix. And then you just do elementary row operations to get this in that as basically an RREF, right? To look like the identity matrix. And so the first thing we did is take -3 times row 1, added it to row 2. Make sure you check my work. And then negative row 2, and then -2 row 2 plus row 1. And so as you can see, we've now, similar to this through elementary row operations, have the left hand side of that line our identity matrix, and thus the right hand side by our theorem becomes our inverse. So A inverse, which we already knew this because we dealt with this throughout the entire presentation, is -5 3 to -1. Okay, so we are done with section 2.2, and the homework has already been posted. Again, if you want to get those extra credit points, you will turn that in to me Wednesday. I won't even ask for it. You just turn it in. Bye.